दिया था। पहले तो
Hey, Sean, go ahead and check your ability to share stuff. We're going to wait for a few minutes. Check your ability to share your screen, etc. Can you hear me, Sean? Because I can't hear you if you're talking. Oh, never mind. It's my bad. Yeah, no, I thought I'd. Okay, I can hear you, Majid. I can't hear you, Sean. Ishan? Hey, Nishant, are you with Ishan by any chance? Are you in his group? Wait, somebody else speak up, just so I know. I know it's not me and not.
I
Hi.
can hear you.
All right, thank you.
Yes. No, nobody can hear you, Bobby. It's all in your head.
You're pulling my family's tricks on me now, man. We're waiting for Ishan to show up. Is there anybody else from Ishan's group in Mumbai online? Okay, while we're waiting for Ishan to work out his logistics issues, let me tell you what we've got. Um, we've got Ishan here next week. It's Yan Lee from Samsung. I won't be able to join. I think I need to find somebody to volunteer to host. There's a reasonable chance. Oh, Ishan, you're back. Can you speak again? Huh, you got a problem with your mic. You want to dial in on the phone? Or let me send you the phone log and dial information. Hang on. Oof, I keep forgetting where. Does anybody remember where the meeting? Yeah, I assumed you can hear me. We can't hear you speaking for some reason. Okay, so Ishan, I'm going to post a dial-in number into the chat. See if that helps. It doesn't have an India number. Most of it is US, but there's a link to a list of local numbers. It says it has a local number for India, but it doesn't say what. Interesting. There's no local number. It just says it exists. Does anybody know what the local number for Zoom in India is by any chance?
I don't think it's local. I think if my memory serves, it was a toll-free number.
Got it. Okay, let me look for that here. I don't see it. But I think, Ishan, you can dial the US 800 number if you like.
Yeah.
No, you're not audible now it's not working for whatever reason. Or you can try one thing, join Zoom twice, once from your laptop and once from your phone, and use the phone for audio. Do you want to try that? So while we're waiting for Ishan to get sorted out, so we got 12:15, we got Yan Lee. Right now, I don't have a plan for 12:22, and definitely not for 12:29. So there is a white paper I've been working on that I'll make a runtime call next week, depending on what I'm assuming everybody's going to be off for 12:22, right, Joe? Bijan, that seems like a reasonable assumption, right? 12:22 and 29.
Yeah, I think it's mostly shut down.
Yeah, okay. So 12:22 and 12:29, no meeting. 1:05, Mike Bartley from TESOL is going to start an effort to write a testing white paper. So if you want to, he's going to they're going to put their initial thoughts together on 1:05. So if you'd like to participate in that effort, that's a good meeting to show up at. 1:12, Steve Helvey is going to talk about the OCP marketplace. We've got we would like to put in, or Cliff would like to put in a whole lot more information about chiplets into the marketplace, actual products. And so we'd like to create a chiplet friendly process for the marketplace. Steve Helby will sort of talk about what the marketplace is. And the plan is to do it in 2 phases, sort of come in, talk about the marketplace, and then collect everybody's input and come back with here's a proposal for the marketplace. So that'll probably happen somewhere in February or March. And 119, Marek will talk about the business group white paper. We'd like to get that published in February. So 119, Marek. 126, Professor Nick Dust from, I hope I'm saying his name right. Professor Nick Dust from Colorado State will be presenting on their work on chiplets. So, and I also attended the UCLA CHIPS meeting on Wednesday, and there's a lot of interesting work. So for those of you who don't know, for about a year, I've been working in a group called Mr. HEAP, the Manufacturing Roadmap for Heterogeneous Integration and Electronic Packaging. And the Mr. HEAP group did its final report out. It was an advice group for NIST on how to sort of bring packaging back to the United States. And the person who led Mr. HEAP is now the director for the National Advanced Packaging Manufacturing, NAPMP, for the Professor Subbu Iyer. So we had the report out, and I'm going to invite the other groups from the technical working groups from the Mr. HEAP report to present in February. And one of the things I would also like, as an offshoot, we've been working on a modular reference architecture for HPC, John Schaff and I would like to kick off a modular architecture development effort. I've been socializing this one-on-one with several companies with a fairly positive response. So I'd like to kick off that effort in the new year. So I'm going to save a slot for myself somewhere to talk about it. So if you have people, please send them our way. I'd like to slot them in starting February and March. Ishan, is your audio issues worked out?
Yeah, hi Boppy, am I audible?
Fantastic. All right.
Okay.
Hey, Bobby, it's Cliff. Just wanted to, I jumped in a bit late, so I was just wondering if you managed to mention the Chiplet Summit and that
Nope,
week's.
I didn't. Thank you. Actually, I did in yesterday's meeting at Thursday. I forgot here. That's a shame on me. So Cliff and I are again putting together a. Are we calling it a workshop, or are we? What are we? A
Yeah,
3 hour thing.
same. They call it a tutorial. We call it a workshop.
Okay, a tutorial workshop for 3 hours, right? We're not going to extend it beyond 3, right? For 3 hours. So we'd like to highlight work that we'd also like to synchronize a bunch of announcements at that workshop. So I think we're going to release the CDX paper. We're going to release the business white paper, hopefully the control flow spec, which if it ever gets, if I can get my act together. And there was one more thing I forgot. But anyway, and if you'd like to, if you have a thoughts on anything you'd like to talk about at the workshop, just drop us a note in terms of, and maybe we'll announce a test white paper if it gets, reserve a slot there for the test white paper. So if you have anything, please tell us. And the second thing is we have a booth, right? Cliff, do you want to talk about that or not yet?
Sure, Bobby. We're going to have a 2020 booth for the OCP, and we will have some space for some potentially tables with technology demonstrations, but they have to be demonstrations for things that would not go in a booth commercially, because we can't cannibalize what people might pay to have a booth for in our booth. So there could be some opportunity there to have a tech demo, something that's really pre-product that we could consider putting in our booth, and people should let us know if they have any ideas.
So right now I've got 2 demos from the Department of Energy, likely 2 demos, and 1 from UCLA lined up. So I think we can fit in 5, Cliff, or you think we can fit in 8?
I'm not sure if I'm sure we could get at least 1 more in. I think we'd have to check the layout, but we'll have like a 10 by 10 area. So, you know, 4 or 5 tables, I think, depending upon the size of each demo.
So so let's assume 5 for now, and it's our usual buckets. It's either actual chiplets, workflow, or IP. And Ishan, I'm very excited to have Ishan. He's graduated from are you well, I don't know if you graduated yet.
I have 6 months to go.
You got 6 months. All right. Professor Gupta's group in IIT Mumbai, IIT Bombay, but the city is Mumbai. And I'm very excited because we have this one beautiful tradition of like publishing work that's done in the ODSA, and Ishan's work continues that trend. I know Jawad does, and this is work that led by JP in the package work or open package effort. All yours, Ishan.
Yeah. Good evening and good morning, everyone. So this particular work that I'm presenting here will be for the power integrity analysis for interoperability of both chiplet interfaces. So I'm Ishan Mishran. I'm currently master's student doing integrated circuits at IIT Bombay. So this is our group, high-speed integrated circuits and communication systems group. So this is our group of members where we've done certain electronic and photonic IC tapeouts. And this is some of the work described better. So we're doing work on high-speed ICs for chip-to-chip interconnects in SerDes. Then on high-density interconnects also we work, and we've also done prior work on analog mixed signal and RF ICs. This image on the right is of a photonic IC done by one of our ex-PhD students. So now I'll get to the work done in this particular paper. So what I'll be covering is the introduction. Then the introduction will be covering basics of what chiplets are, if people are not very well aware of it. The problem statement, which is why we do power integrity analysis. Then I'll cover the package layout, then the modeling, which will cover in very brief the PCB package and dies modeling. Then the methodology, which would cover how to improve and analyze power integrity and whatever challenges we face during that process. Then I'll cover the results, conclusion, acknowledgement, and references.
Hey, Ishan.
So here's the intro.
I just want to say
Yes.
DJ is not here, but there's a great DJ helped fund this. They get the funding through Meta, so eventually we'll get him to start attending our meetings again. But if hint for anybody else from a big company, if you can fund a university for this work, we'd love you. So sorry, Ishan, go ahead.
So what is power integrity? So PI is basically, it's a way to check whether a desired voltage or current is being supplied to its desired destination from the supplier. So since there is a rise in data rates and decrease in supply voltages in the high-speed I/O applications, the importance of robust power integrity at the die, package, and board levels has intensified. Now, this challenge is also compounded by more stringent noise specifications, making effective management of PI increasingly vital as for the same noise levels, our SNR has reduced since our power supply has reduced. So this work here presents a framework. Just a minute. Yeah. So this work here presents a framework for analyzing and enhancing the PI in high-speed or high-intensity die-to-die chiplet interconnects. So chiplets are basically small, independently designed and manufactured dies that can be interconnected to form a large SoC. Now, what is the motivation behind this? Is that since Moore's law has been saturating, so for scaling up transistors for better performance, but with the same transistor density, since we are saturating in terms of Moore's law, we need to increase the size of the chip, but this is limited by our fabrication process as bigger chips have a lower yield and the cost of increasing the number of transistors on a chip increases non-linearly. So this is where the new concept of chiplets, that is heterogeneous integration or multi-die technology, comes in, where we partition our SoC into several tiny dies and then we reintegrate them. So how this benefits us is that we can overcome these size limitations that monolithic dies are offering, and we also improve the yield and the time to the market also gets accelerated. Now, recently, since most of our applications in these high speed are surrounding these high speed IOs, so in recent times, two new standards have come up for these die-to-die chiplet links, them being a bunch of wires known as BO and Universal Chiplet Interconnect Express, UCI. This particular work showcases the interoperability for 5 chiplets from 2 independent implementations, that is from Blue Cheetah Analog Design and D-Matrix. So we have followed the BO 1.2 standard here at 16 Gbps, which was set by the OCP, Open Compute Project, Open Domain Specific Architecture, which is led by Mr. Boppy. And this is the main introduction of this project. Now, the problem statement is that the main challenges, like I earlier said, that it is, since the supply voltages are very low, like around 0.75 volt or lower, achieving good power integrity is very difficult. So the main reason behind this is that the switching at these IOs cause very large current transients, which can cause supply voltage noise. So this image here is an example of how supply voltage noise would look on an oscilloscope if you would try plotting it for a for an IC that is currently switching continuously. Now, the main contributor to this power integrity or the supply noise is the simultaneous switching noise. So SSN is basically a phenomenon that occurs in digital ICs when multiple circuits switch states simultaneously, leading to unwanted transient voltage fluctuations on the supply lines. So SSN adversely impacts these circuits, causing voltage instability, data integrity issues. So eliminating this problem for transceivers or let's say SerDes high-speed I/O systems, it's very important because these could lead to a high BER, like a bit error rate, or even a lower jitter tolerance. Now, as we know, we can see that there can be parasitic inductances between the package and the IC, and even between the PCB and the package. So any These inductors, they have a property to resist any change in current, which is why these are of great importance in making sure that the supply noise is eliminated. So since you go at higher and higher speeds, the switching speed increases even more, because of which, as you know, our voltage across the inductor will be directly proportional to the rate of change of current. So since at higher speeds, this rate of change is much faster, the drop in the supply voltages could be greater. So this is a layout of the package. So this is basically the test package, or we even call it the Bow interop package, because we're using two vendors, that is D-Matrix and Ruchita Analog. So this was a 40 cross 40 millimeter 12 layer package that used these two dies from D-Matrix and BCA. BCA would be in blue cheetah analog, which I'll be using again and again in this presentation. So here we have 5 test structures. So the first test structure was between D-Matrix and D-Matrix, and this was a 20 millimeter bump-to-bump long channel. The second test structure here was between blue cheetah analog and D-Matrix. Again, this was a 20 millimeter bump-to-bump interop long channel. The third test structure was varying from 5 millimeter to 10 millimeter because of this 90-degree bend, and this was between two BCA dies. The third test structure was a short interop channel of 5 millimeter, and the fifth one was a long channel between two BCA dies. So what we did was we analyzed the power integrity of each test structure individually and met the given specifications provided by D-Matrix and BCA. The packaging technology used was FCBGA, which is flip chip ball grid array. So flip chip ball grid array is basically a type of IC packaging technology which is used in semiconductor devices. So what happens here is that our actual IC is flipped upside down and attached directly to the substrate or the circuit board, and the connections are made through an array of solder balls at the bottom of the package. Now the process nodes used for they weren't used, but the plan is for the BCA and DM is to use 12 nanometer technology for the blue chip analog dies, and D-Matrix would be using 6 nanometer. And the size of the dies would be 2.5 cross 2.6 for BCA and 1.28 cross 3.26 for DM. The critical power nets during this power integrity analysis were the VDD digital, also abbreviated as VDD core, VDD-C over here, VDD IO, and VDD analog. So the range of the supply voltages were 600 to 900 millivolts, and the peak current that you were expecting for these supplies were roughly 2000 plus minus 500 milliamps. So here's the modeling section. So this briefly describes how these components would be modeled, that is our PCB or our bulk, the package, and the die. So the power delivery network here, which includes these three, were to be modeled individually by the suitable models, and then we'll be stitching them together more like a linear network. This helps us understand how the power delivery network of our entire system is. So first, I'll briefly discuss the PCB modeling. So the PCB's power delivery network was modeled using a pre-layout modeling technology, which was based on an application note and spreadsheet tool provided by Intel. I've provided the reference towards the end. And these are basically distributed RLC models, like a pi model was designed using the tool that Intel had provided. And also this also helps us because the frequencies that a PCB are effective to are basically less than 50 megahertz. And however, if you have an advanced PCB designing tool and if your PCB is ready, you can also extract an S parameter model for your PCB and use that as a black box to model it. Now for the package. So modeling complex packages with a lot of interconnects is definitely going to be challenging because you can't just do it with a lumped or distributed model because you will have your BGA balls and bumps, etc. So S parameters is the most practical approach in such a scenario because these capture various effects like your dielectrics, conductance, vias, bumps, crosstalk, etc. And like I said, for the PCB's case, you can just treat this S parameter extracted model as your black box during the analysis. This is one example of how it would look like. So for example, this was the extracted model of the first test structure. So here we had 13 ports extracted. So if you see for VDD analog, we have 3 ports. One going for the BGA that would be connected to the PCB, and then we have for the first die and the second die. Since test structure 1 included 2 D matrix dies, so we had 2 VDD analog ports for the first die and the second die. But they had a common point for the connection to the PCB. Similarly, for VDD-Q, we had 3 power nets or ports, power ports, I would say. Then for VDD-IO, we had 3. For VDD core, we had 4. For VDD core, what the case was that if both the dies had their individual connection to the PCB through the BGA boards. So we had 2 BGA connections here. This is for test structure 4, this extracted model. I'm trying to help the audience visualize how it would look like. So here we have blue chip analog and D matrix dies. So here we can see for the 1.8 volt, we have one BCA power port and one D matrix power port and one BGA power port. And the same is applicable for VDD-Q, VDD analog, the VDD clock. Here VDD clock was specific only to the blue chip analog die. And the same case as before for VDD core. Now, for modeling the die, a power pin of a die is mainly represented. A power pin of a die is mainly represented by a lumped single RPC model, which would represent the die since it would be a very small sized model. So we typically model it by a series RNC, and the capacitance would generally be about a nanofarad, and a few tens of milliohms would be enough for the resistance. So here, this was the model provided by D Matrix for their 3 power ports, VDD analog, core, and IO. So here we had a 1.5 nanofarad and 40 milliohms RC, here 1 nanofarad and 50 milliohm for VDD core and IO. So this modeling is basically enough when the PI analysis is to be done in terms of loop inductance analysis. If you just want to evaluate the loop inductance, which I'll cover in the next section, this RC model is sufficient. But if you want to, I think somebody's mic is turned on.
Yeah, unfortunately, I'm not logged in as host. If you wouldn't mind muting if you're not speaking.
Okay, I think there's no disturbance now.
All right,
Yeah,
I'll
so
log
if
out and come
we
back. Worst case. Keep going, Ishan. I'll log out and come back in with host privileges.
okay. So if we want to go for, let's say, our transient simulations or noise simulations, again, I'll cover this in the next section. So in that case, we might also need to use a current profile as indicated in these figures. So this is how we model our die. So now I'll cover the methodology. So the first thing in the methodology is how can we improve our power integrity. So here, this particular image is the layout image of the 4th test structure. So here in this red, we can see we have a blue chip analog die. Here we have a D matrix die. And also this tool that I've used here is SI wave from ANSYS. So if anybody wants to, like I forgot to mention the tool's name, so it's SI wave if anyone wants to refer to it. Now around this particular die, we can notice that, before that I'll discuss about the decoupling capacitors. So the first way of improving the power integrity is to use decoupling capacitors. So decaps basically help mitigate the power supply noise by providing a low impedance path for the high frequency noise. So this high frequency noise bypasses the sensitive components on your circuit. And also these capacitors will have a tendency to rapidly discharge or charge. And this helps stabilizing the voltage levels. Now, for example, I highlighted these 2 dies for you. Now we can see that I've highlighted certain decaps as yellow and some as black. So the ones in black are your bottom side decaps on the underside, or it's even called the line side of your package. And the yellow ones are your top side decaps. So we can see that the yellow boxes are a bit far away from your red box of the die. That is because the line side or the bottom side decaps can be placed just on the underside of your die. So These are usually preferred because the distance between your cap and the power port on your die, or let's say the bump on your die, it's very small. So these are usually preferred over topside decaps, because the more the distance, again, you will be adding more inductances, which will again lead to supply noise getting increased. But the trade-off here is that if you want to put more and more underside, bottom side or land side decaps, you have to replace them with you have to replace BGA balls that are on the underside with these decaps. So removing more and more BGA balls leads to more IR drop. So I'll show this in the next image. So this is how a cross-sectional view would look like. You would have your IC sitting on the top. This would be, let's say, your flip chip. So here you would connect it upside down, and you would connect it to the substrate using these BGA balls. Then you would have your package. Now here you can see that we have these BGA balls here. So there would have been, let's say, around 3 to 4 BGA balls sitting over here, but I removed them. And I mean, the layout engineers would remove them and replace them with these package decaps. So removing more and more of them lead to more and more IR drop. But so you have to, you will end up reaching an optimum point where if you remove more BJ balls for a bottom side decap, you may not get an improvement in your power integrity. Now, the second way of improving your power integrity is by improving your package design. So the main aspects of the package design are your power planes, ground planes, core vias, and how these help is that the power planes, ground planes and core vias, they're very pivotal for enhancing PI. So they provide low impedance pathways for your stable power distribution. They minimize your ground loops. They reduce your EMI, and they efficiently connect layers to suppress noise. Now, the third point, which will be important while working on your power integrity, is to evaluate the impedance plots. So what we typically want is a flat input impedance plot at the power port to ensure stable power distribution. So if the more flatter your impedance plot is, the more you can be confident that you are going to get a stable and consistent power delivery network, and the variations in your voltage will be even lesser. Because if you have a lot of variations in your impedance at different frequencies, your circuit sees different impedances and will not behave linearly. Now we'll move to how do we analyze our power integrity. So like I earlier discussed about a transient or noise simulations. So that this is the most robust technique of evaluating a power integrity. So what the transient analysis evaluates is that it evaluates the voltage fluctuations during dynamic events by simulating a circuit's power delivery network with a die level current excitation. So this current excitation would account for load changes and switching activities that could happen in a real case scenario. So what we do here is we will be interconnecting, like we had modeled earlier, all the die, the package, and the PCB individually. So now we'll stitch them together, connect them together. And the node that we evaluate is at the
Can
die
I
level.
ask a quick question?
Sure.
Is your die considered the single point source or is it distributed?
It's
Like
a
the
single point source, just like in this particular case. So this is how we have modeled it. I'll come to the exact figure as well, the screenshot from the simulation. So we're basically modeling the die. Like every power port would be modeled by one RC and a current source in
well,
parallel.
big dies now, like, are very distributed, right? You may not have a uniform current across that die. I wonder if you're able to,
Yes, but in this case, we did not have our IC ready. So we just made it a simple model by just using a
okay,
lumped RNC. But in the
okay,
case, let's say we have a proper full flash tape out going on. So we would have our IC analog team, which would have designed their IC. So we could use that directly to simulate and see the problems that could occur.
okay, very good.
Yeah, sorry for the interrupt. What is your package material? Substrate material.
Yeah, just a minute. I'll just, I can't recall the exact. Yeah, so we've used this ABF material. This
Okay.
ABF is your Ajinomoto build-up film. I'm not very aware of the technicalities of the material, but I just had the name noted down.
Okay, sure. You mentioned here it is a transmitting the signal. It will be a parallel or serial. You see, it will be my assumption. It will be serious. What your progress on this?
You mean the current source over here?
Yeah, current sources as well as you need to transmit the data also, no, at the same path.
Actually, the current here is actually trying to emulate the data pattern. So this is a current source is actually generated from a PRBS, which is ranging from 0 to 40 milliampere. So it's covering all the scenarios where you might have like a number of IC blocks demanding current at a given time. So it covers all those possibilities. Is that what you're trying to ask? I mean,
Yeah,
this is
yeah.
not a
I will.
constant current source. Like you might, in a let's say in a SerDes block, you might have random data sequences. So this current is a random data sequence itself, ranging in this current range.
Okay.
Does that answer your question?
Yeah, yeah. I will look out.
Okay. Okay. So, like I said, we had modeled the die package and PCB individually already. So, if we want to go for this transient analysis approach, which is recommended, the node that you should be plotting while checking out your supply noise is between the package and the die, basically at the junction between the package and the die. That would be your bump. But this node should be towards the side of the die of the bump. Like the bump would have two sides, one end towards the package and one towards the die. So since the bump would have its own inductances, which would be incorporated inside the package as parameter model, so you would be checking it on the side of the die. Now here is a screenshot from Keysight ADS on which we had done the simulations for the power integrity. So here's a test setup on the left. So here we can see this particular part is the package model, which is a rest parameter model of the package. On the right side, we have our PCB Pi models, which was generated using the tool provided by Intel. And these four over here are basically slices. So here each slice uh, represents the die. So if I go inside a particular slice here, you can see in this image we have VDA, VD core, and VDQ. So if I go inside these, I get these three power ports, and within them, I have my RC model here. So this is my 50 milliohm R and 1 nanofarad C. So here, this AC current source is basically in case I want to evaluate the loop inductance, I want to see the impedance plot. So I would use the AC current source and plot the impedance seen from the die. And here, if I want to do the transient analysis, I'll be using this current source. So this current source, this random data sequence in the form of current was provided by D matrix itself. And also this particular method for analysis, which is this transient analysis, was done only for the D matrix dies. Since Blue Cheetah Analog did not provide any RNC models for their BCA dies. The second method is the loop inductance analysis. So this method basically analyzes or assesses the inductive effects of your current paths, identifying and minimizing loop structures to reduce the voltage fluctuations and enhancing the overall system reliability. So this is an image that could help the audience visualize what would the loop inductance constitute of. So you would have your IC here, you would have various inductances across your package, across the power plane and the vias. So this particular entire loop is what your loop inductance is, and the use of decavs basically reduces this entire area. And this is the main motive of this loop inductance analysis, is to evaluate how much of a loop inductance is your package offering right now, and is it meeting your spec or not. So in this method, we basically extract this, like we have this parameter model already ready. So you would excite it, like I showed it in the previous figure, you would excite it with the AC current source and you would evaluate the impedance at that particular point. And usually the frequency band that we measure for loop inductance in packages is around 20 to 50 megahertz, because it's up to this frequency that your package decaps would respond to, which would typically be a few microfarads or maybe hundreds of nanofarads. And the loop inductance can basically be improved by optimizing your capacitor placement, your via positioning. These optimizations could help mitigate high loop inductance. And
Do
yeah,
you
by
include in those decaps, do you include things like, you know, the series the series inductance with the cap, the and R, and or it's just a
yes, no, we take a practical model of the decap, which would we actually the decaps are modeled by a two-port S parameter model. So that is how we are modeling these decaps. So it does include your ESL and ESR.
Okay.
I have one more doubt. You connecting one chip to one die, it will be connection through in the substrate, or you are using any interposer technologies?
No, it's happening within the package. The dies,
You are
the
making
dies
the
are being, yes. Yeah, so the dies are interconnected within the package itself. And go back to the layout. So if you go here, we can see that we have one die on the left and on the right. So these are connected within the package. So the package over here, this is a 12-layer package over here. So this already includes your vias and power planes, etc. So the dies are connected within the same package. We are not using an interposer.
okay. What is your package dimensions?
40 cross 40 millimeter.
Okay. Okay, sure. Thank you.
So here are some challenges that we faced during the analysis of the PI. So the first challenge that we faced was the convergence problem. So for some S parameter models of the test structures, initially we faced these convergence issues, and like you can see, we can see these rising oscillations during our time domain or transient simulations. So this was happening even though we had ensured passivity during our S parameter extraction. So to address this, what we did was we fit a broadband spice model to that extracted S parameter, which had resolved this issue. Now, usually why this happens is that
Your
we could,
y-axis has the wrong units, or should be
sorry, sorry, can you repeat your question?
your y-axis, I'm saying, maybe has wrong units. Should be millivolts, right?
No, it's actually kilovolts. It actually rose a lot, and this is where the simulation had stopped because it went above its like ADS couldn't simulate further. So it's actually in kilovolts.
Oh, how is that? You're saying you have an unstable system?
Yeah, yes, that is the challenge I'm actually discussing, that it wasn't converging. So there was actually
I see.
in some of the extracted S parameters, there was some negative impedance that was probably detected, due to which there was amplification. And to get over this issue, we had fit broadband spice models. So like you can see, so our this BO 1.2 standard is at 16 Gbps, and we can see this time is still 30 nanoseconds. So 16 Gbps would um, be in maybe some few picoseconds. So this is after maybe like tens of thousands of time periods. So that's why because of consistent amplification, this voltage has risen a lot.
Okay.
So basically, when we fit a broadband spice model, it's basically fitting that extracted S parameter to a multipole RLC model, which ensures that there is no passivity because only RLC components are used to model it. Then another challenge we faced especially in the blue chip analog dies, were the high loop inductance. So initially they had exceeded the loop inductance had exceeded the provided specifications, and we had addressed this issue by enhancing the package design. So in the design, what we had done was we made modifications like additional core and ground vias were added, and we made some changes to the power planes, and these were enough to reduce the loop inductance by about a half. By a factor of 2, they were reduced. Then the second issue was the chip package resonance. So this mainly occurred because there was a frequency artifact in the initial current profile provided by D-Matrix. So the first current profile that was used had significant frequency components that were in line with the chip package resonance frequency. So why this resonance occurs is that, as you will see in the impedance plot later, is that the inductance of your package and your dies or your chips cap, they can resonate with each other, and at that particular resonance frequency, if you have any uh, let's say a frequency component of your operation, so that could cause a lot of lead to a lot of noise in your particular system. So the issue that happened initially was because the initial current profile provided was generated from a PRBS7 source, and uh, those the D-Matrix employee had stitched those sequences like in a periodic way, like they were just it was a repetitive PRBS7 sequence. So because of that, we had this frequency artifact, and then later he generated a longer sequence, and instead of stitching multiples of the same sequence, and that had resolved this issue. Then the other issue was the noise aliasing issue. So what was happening here was that initially we had taken a small time step value of 100 picoseconds while simulating, and we were seeing a lot of noise, supply noise around 50 to 60 millivolts peak to peak. So upon reducing the time step, because we weren't expecting this noise, even though we had taken all necessary measures. So I noticed that in reducing the time step value to about 10 picoseconds from 100 picoseconds, the noise came down to 5 to 10 millivolts. So the reason I could figure out here was that maybe there would have been some noise aliasing, because with the higher time step value, you have a lower sampling frequency. So maybe there wasn't enough bandwidth for it to sample all the points in the simulation, because of which noise had folded back into its uh, bandwidth, and it came out to be a lot of noise. So here is a summarized PI analysis flow. So the first thing that we would be doing is you would extract your S parameter on SI wave or any other tool of, let's say you have power SI from Cadence. You would extract the model of your package, and you would include your PCB models and your die model, your current profile, and you would simulate it on ADS or any other similar software. After the simulation, you will measure whether your loop inductance or peak-to-peak noise on your supply specification is met or not. If it's not, you either work on your PCB model and see if you can improve that, or you verify your die models with your chip design team, or you check your current profile again. If these seem to be all right, then you might have to, the only option left would be to improve the layout of your package, and then repeat this process in an iterative manner till you meet the specifications, and then you are good to go. So these are the results for the D-Matrix die. So the 5 test structures were basically analyzed for 3 values of decaps: 5.1 micro, 1 micro, and 4.7 micro. So as one of you had already asked, if I'm including ESL or ESR, so the parameter models of these decaps were basically used. We had S2P files for each of these decaps to take into account its equivalent series inductance and resistance. And among these 3 values of decaps, the 4.7 microfarad decap had given us the least peak-to-peak supply noise. So this is an example of how the supply noise looked like after the simulations on EDS. This is for the fourth test structure. So this is for VDD core, analog, and VDDQ. So these are how the supply noise would look like, which is very similar to the image I showed earlier from a real life oscilloscope. Here are the input impedance plots as seen from the die. This is from test structure 1, without and with the 4.7 microfarad decaps. So I'll just describe the labeling on the plot first. So here we can see that there is a rise in your impedance. So this rise would basically mean you have a inductive nature. So this inductive nature is coming from the PCB model that we had. It obviously included RLNCs. So the nature of the PCB during this in this frequency range of about of hundreds of kilohertz is inductive, and then we have a package decap that makes it capacitive during this frequency range. Then after that, it is the package decaps ESL that kicks in, and that keeps increasing your impedance. And after this particular point of, let's say, 100 to 200 megahertz, you have your die cap kicking in, and that brings it, it reduces your impedance. Now, I also discussed the chip package resonance property. So if I go to the first figure on the left, which is without the decap, we can see that the chip package resonance is pretty significant. For example, if I look over here, like here we have our ESL or the inductance from our package, and here we have our cap from the chip or your die. So these are resonating with each other and providing a very high impedance. So if you have a frequency of operation along this particular line, you would see a lot of supply noise. So here we can see that um, the resistance around this point is close to 20 ohms at the chip package resonance region. And over here, upon using the 4.7 microfarad decap, it's reduced to about 2 to 3 ohms. So we can see a significant drop in our impedance over here, and this also relates to your loop inductance. So your loop inductance will basically be the slope of this particular curve. So given that this point is constant and this point is reducing, so your slope also reduces by roughly the same factor, which is about a factor of 5. There's a reduction of in loop inductance by about a factor of 5. So that this plot also can explain you the importance of decaps in improving your PI. This is the impedance plot I seen from the die for the fourth test structure, D matrix die, with and without the 4.7 microfarad decap. So here also we can see a very similar nature, that we had a peak impedance here of about 8 ohms, and that reduces to about 32 ohms upon using your decap. So these are the final results for the D matrix die. So here are specification for the different power units. Like for VDDQ, we had a spec of 20 millivolts peak to peak. For VDD core, 10 millivolts peak to peak, and for analog, it was 10 millivolts peak to peak as well. So this was the supply noise we had before placing the 4.7 microfarad decaps. So we had not met the spec for VDDQ and VDD analog. For VDD core, the specs were easily met. But after using the decaps, there's a significant drop in the supply noise by roughly 3 to 4 times. I'll just hold this slide for about 5 to 10 seconds if people want to have a closer look at the numbers.
Hey, you're coming up on 5 minutes, okay, Ishan?
Okay.
You're going to
Okay,
lose
I'll
we're going to lose the audience at that point.
Yeah, sure. So this is the results for the blue chip analog die. So here we had only evaluated the package loop inductance, as I earlier said, since we did not have any die RC models or any die model for the BCA dies. So here we excite every power port with an AC current source, and by grounding the BGA ports, so we can either ground it or use a small bypass cap. Either would work. So here, since we have no die RC values, so we don't see any dip in the impedance over here. This goes on a consistent rise because of the ESL of your package. So we see no drop in your impedance because there's no capacitive nature of the die coming here, since we have not included any die RC. So here we calculate the loop inductance across this loop in the around 10 to 50 megahertz. That is roughly around this range. And these are the results of those loop inductances. So these are the specifications provided for VDD core 200 for 1.8 volt analog and clock. We had 400 picohenries specification, and for VDD IO we had a spec of about 200 picohenries. So this was before we made improvements in our package. Like I always said, we had a lot of loop inductance initially. So this was before we made improvements in our package, and after including our decap and improvements in the package, we saw a significant drop in your loop inductance.
Hey, Ishan.
And these numbers.
I apologize. I'm going to make an unrelated interrupt because we might lose people within a couple of minutes. I'm going to borrow 30 seconds of your time. Hey, the call for papers is out for the regional summit in Lisbon in Portugal. If you submit a paper there, you'll have to take one. Excuse me, a proposal for a talk there. You'll have to take one for the team and travel to Portugal in April. So we need Cliff here, who's online, wants lots of proposals, so we can create an ODSA specific chiplet session. Thanks, Ishan. Go ahead. I'm sorry.
Yeah, so that was all in paper. I'll just conclude it quickly. So this work basically, it shows the PI analysis of BO5 chiplets implemented in this Bo interop package. And this is unique because other literature work doesn't discuss the PI for chiplets, and people generally don't have an idea of what specs can they expect, how to model the die in such cases. So also the PI specs were also met by reducing the package loop inductance, careful placement of the vias, and optimal selection and placement of the decaps on the die and BGA sides of the package. That is the top and bottom side of the package. And this modeling and analysis methodology can discussed here in this presentation can help readers understand how to analyze and ensure a good PI for the given design. So also I've Mr. Boppy had already mentioned that it's been accepted at a conference. So it's been accepted at India's largest conference, that is VLSID 2024, and it's affiliated by IEEE. And here are the co-authors. So the first co-author I would like to thank is JP. He's helped me a lot throughout this project, and then he's a member from D-Metrics, and then Vincent from DM, then Elad Dalal, who's the founder of BCA, then Srinivas from Meta, then Mr. Shalabh Gupta, who's the PI and professor in this from IIT Bombay. Then the technologies, I'll be mentioning Mr. Boppy, who's the project lead for OD from ODSA. Then DJ from Meta, Irene from DM, Praveen Meenakshi, Mike from Tissol, Namoon from Google, and Shekhar, Rajshekhar, and Midhun, who are fellow members from my lab in IIT Bombay. Here are the references I used in this work. Yeah, and thank you.
Hey, and Ishan and JP, the analysis is available for anybody who wants it, right? That's on a Google Drive, and people can ask for access.
It's available, but it may not be in a very systematic manner. It might be a little jumbled here and there, but it's available.
If JP or you or Ishan could please post a link to that drive, I will include it in the minutes. I know I have it, but if you wouldn't mind.
Sure, yeah.
Anything else you want to add, JP? This is wonderful work.
Yeah, thank you, Ishan. This has been excellent work, and thanks for consistently working on this project for multiple months to get to this point. Thank you.
Yeah, thank you, JP, for your inputs and guidance.
Sure.
Any other questions? In that case, Ishan, you're in great shape for your talk on at the conference. This is very, very well done. Thank you.
Yeah, thank you, Boppy.
Yeah, so thanks, Ishan. I'll send out a link to the recording. And again, don't forget to submit papers to the regional summit. Otherwise, Cliff will come look for you. If there's nothing else, we're done. Top of the hour. Thanks all.
Thank you.
Yeah, thank you everyone
Bye.
for attending.
Thank you, guys.
Thank you. Bye.
It's 10:30, right, in India?
Yes, Poppy.
Ah, well, Friday evening, 10:30. Thank you. Bye.
Yeah, bye.